Hello, everyone, and welcome back to our next talk with Avi Rubin. Dr. Avi Rubin is a professor of computer science and technical director of the Information Security Institute over at Johns Hopkins University. He is also the director of the JHU Health and Medical Security Lab, and prior to joining Johns Hopkins, Rubin was a research scientist at AT&T Labs. He is also the founder of Harbor Labs, a cybersecurity company, and Rubin has testified about information security before the US House and Senate on multiple occasions. And he's the author of several books about computer security. Rubin is also a frequent keynote speaker at industry and academic conferences, where he has delivered a widely viewed TED Talk back in 2011 and another back in 2015. He has also testified in federal court as expert witnesses on numerous occasions in matters relating to high-tech litigation. And with that, I introduce Dr. Avi Rubin, where he'll talk about medical device security.
Well, thank you for that introduction, Michael. Let me just switch to a screen share. Okay. So 1 second. Are you seeing the screen that you should be seeing, the full presentation mode?
Yeah, we see it.
Okay, great. So I appreciate being invited to this event. I understand you guys are in Michigan mostly, or the event is hosted in Michigan. And I went to the University of Michigan myself, got all my degrees from there. So it's a little bit of a homecoming, although I'm here in Baltimore over Zoom. That's the way things are going this year. So let me tell you a little bit about I'm going to talk about medical device security, and I'm going to tell you a little bit about, before I start, how I got into medical device security and what my interest is in that. So at Johns Hopkins, I started a lab called the Health and Medical Security Lab because I was working on electronic voting security. And when you are at Johns Hopkins, everyone knows that we're a really big hospital and a really big medical school, and that pretty much any computer science work that you do eventually is going to look at medical applications, because that is really the 900-pound gorilla at Johns Hopkins University. And so I worked with several colleagues and got a grant to work on medical security, healthcare. We called it THAW, Trusted Health and Wellness. And in my lab, I started training a bunch of students to work on medical devices and to do their research on medical device security. And when those students were getting ready to graduate, they joined my company. I had formed a company called Harbor Labs. And Harbor Labs started to work with the medical device security industry, or medical device manufacturers who were looking to have security. And so the case studies that I'm going to talk to you about today, towards the end of this talk, have to do with things that Harbor Labs encountered with our clients and things that we did for them in the space of medical device security. So let's jump right in. So I want to start off by telling you how we got to where we are today. And we're looking at different phases of cyber attacks. So in the very beginning, the earliest form of hacking, basically hacking had to do with people sitting in a computer somewhere or launching scripts and attacking other cyber installations, trying to break through firewalls, trying to get malware installed on computers. And the attacks were digital, the targets were digital, and everything existed in the digital world. The next step towards where I'm heading is the combination of cyber with physical systems. So this is like critical infrastructure, dams, water supply, all of the things that are really tangible in the world. So they're not like attacking a server or stealing data from somewhere, but they have to do more with things that we can physically experience. And so we call that the physical epoch. And the last one is kind of the combination of those, where we look at digital attacks against the actual human beings. And that's the focus of what I'm going to talk about today, because medical devices can be connected to people. And then if you attack the medical device, you can impact that person's health directly. So let me look at the second epoch that I talked about, which is the cyber physical, before we get into the medical. So here was a headline in the New York Times, And it had to do with an incident that occurred a couple of months ago, in fact, 2 days before the Super Bowl, and it happened near Tampa where the Super Bowl was being held. Sodium hydroxide is found in drain cleaners, and it's an agent that's used to purify water, but it's used in quantity of 100 parts per million. And an attacker had basically used some remote access software to hack into this water treatment facility and change the variable that determined how much sodium hydroxide was in the water from 100 parts per million to 11,100 parts per million. So really going from what's a safe amount to something that would be deadly and that would actually kill people. And the way this attack happened is that employees were sharing remote access credentials that they weren't supposed to share with each other. And there was a system they were using called TeamViewer, which is kind of a collaboration tool. And that had been configured incorrectly. And so these remote access credentials being compromised, along with the misconfiguration of TeamViewer, allowed someone to take remote control of a system that controlled how much sodium hydroxide there was. And so that could have been really, really serious. And so the first question that comes to mind is, why did the system even allow a value like 11,100 when it's supposed to be maxed at 100? You would think that some safety thresholds would be in place so that nobody could ever change a value so seriously. Luckily, this was caught because there was a system administrator who actually sat at their terminal and observed the cursor moving across the screen, some selections being made, because with remote desktop, if you're at the machine that's being controlled remotely, it looks like someone's there doing things, and saw this happening right in front of their own eyes. And so raised the alarm, and this was fixed. The attack was prevented, but it could have been really, really serious, like perhaps one of the most serious cyber attacks we've ever had. In fact, I was staying with my family in Florida at the time, maybe like 50 miles from where this happened. And so I don't think we shared that water supply, but it's pretty scary to think that this was going on right there, right before the Super Bowl. So let me talk for a minute about vulnerabilities and how a vulnerability, how the risk of a vulnerability can be perceived over time. And I'm talking about like a software vulnerability that could be used to maybe take over a system to generate an exploit or something like that. So initially, the vulnerability is undiscovered. So there's no risk. Nobody knows about the vulnerability. And there might be a little bit of risk, but the minute somebody discovers it, it's no longer in the undiscovered state. So there really is no risk. Then somebody discovers the risk, so this vulnerability. So at that point, we may actually have a problem because the vulnerability has been discovered, and the person who discovered the vulnerability might want to exploit the vulnerability, and that would be bad for whoever was targeted by that. The next thing, let's say that this person that discovers the vulnerability is actually a good person, and they go and they disclose it to the vendor who wrote the software and say, you need to fix this vulnerability. The risk is slightly higher at this point because more people know about the vulnerability, even though some of them are at the manufacturer. Once this type of thing becomes known, it's hard to kind of keep the genie in the bottle. The information about it starts to spread. And here's something that is pretty ironic. Once the vulnerability is patched, we actually have a much higher risk. And that may be counterintuitive. You'd think if there was a patch for the vulnerability, then there's lower risk. But the thing is that the patch actually gives a lot of information to attackers about this vulnerability. So one thing that happens is there are attackers who sit around looking for new patches. And then they find the patch, say it's for a particular piece of software, they can reverse engineer the patch and figure out what was the vulnerability that this patch was addressing. And so that makes the vulnerability much easier for people to know about. Now, the next step is often that the vulnerability is published in like a CVE, which is the NIST database for vulnerabilities. And now it could be known to anyone, even people that don't have the skills to reverse engineer a patch. And so even though this vulnerability has been patched, there are probably a lot of people out there that haven't patched their system, and so they would still be vulnerable to this. And finally, the most vulnerability, the most risk happens when attack tools start to incorporate the exploit for this vulnerability. So this is kind of the life cycle of risk relative to vulnerability. And it kind of begs the question, when should you patch a system? If you patch it too soon, you're going to possibly give away the information about this vulnerability to many people. There was actually a research paper out of Berkeley where some researchers showed a way, the title was something like automatic generation of exploit from patches. And so what their tool did was it took a patch, it reverse engineered the patch in a fully automated way. It then figured out what the vulnerability was and built an exploit that took advantage of that vulnerability, all in a fully automated fashion. This means that within seconds of a vendor issuing a patch, there could actually be an exploit for that vulnerability. So all of this is to give a backdrop when I talk about medical device security of how the risk moves around when there's a vulnerability discovered. So let me talk about the era that we're in now in medicine. So let's start here with the leftmost picture. The leftmost picture on the top here is an infusion pump. And when these things were built and invented and designed, they were initially kept at hospitals. And the idea was that you put some medication into the device. You then actually hooked it up to a patient who had needles in them, and the device would dispense the medication. So if the patient is lying there for many days, then a few times a day, perhaps, they're getting some dosage that was determined by the doctor of that medication into their body. Nowadays, there are also infusion pumps that are in people's houses. So it's almost perhaps life-changing, life-saving, the fact that people who otherwise might not have been able to get to a hospital or may not be able to get their medication quickly enough can now get it in their houses. But what happens when this thing is in the house? These devices are pretty advanced and they're pretty smart, and they have internet connectivity, and they have applications where the doctor can monitor remotely and perhaps log into the device, change the dosage, check for compliance, check for the levels of the medicine in there, and basically control the device. So from a cybersecurity perspective, if you think about this, you have a human being with needles in them connected to a device that has medicine in it, and that device is electronic and has internet connectivity. And if you think about the fact that this device might be on the patient or the user's home network, where there may also be a lot of insecure IoT devices, this is a pretty scary scenario. At the same time, this is life-saving technology. And so from a cybersecurity perspective, the idea is that we want to try to build as many safeguards as we can into something like an infusion pump, and test it and red team it and make sure that it's as secure as we can possibly make it. And we also don't want to scare people so that they'll think the cybersecurity risks are so high that they won't use this device when they actually need it, and that would be terrible. Let's move along to the next one. What's shown here is a smart MRI machine, which has an app, and the app can be used on a mobile phone, such as shown here, to see images and patient information, etc. And the reason that I included this one in this presentation is that there's a very large cloud component to many medical devices, and especially this one. So in the cloud, you have information about patients, you store images, and that allows there to be a portal so the patient can log in from home and see this information. The patient's doctor can log in, and also the information can be shared with different specialists. So you might have an MRI for a problem with your knee, and your primary doctor may want to look at it, but then you want a radiologist to look at it and an orthopedist. And by having a system where all of this data is in the cloud, that enables multiple different accesses to it. At the same time, it also means that personal health information is perhaps at risk because it's sitting in a cloud server. That cloud server could be vulnerable to attackers, and that information could be very sensitive. Maybe there are many different ways you could look at an example of sensitive information. Perhaps you're a professional athlete who's trying to negotiate a contract with a sports team, and there's an MRI showing that there's a problem with your knee, that could really affect your negotiation. And that's very private, and that's perhaps one of the more benign examples I could give of why privacy is important for medical information. Let's look at the next example here on the right, in the top right. And here we see an example of what's becoming more and more common these days, which is robotic assisted surgery. So in this picture, on the right of the picture, you can see a table with some robot arms and somebody that's there observing to make sure everything's okay. And just to the left of that, you see two people in medical dress, and they're surgeons, and they are sitting in with their head inside of a computer. And what that is it's a display that shows them, it's from a camera that's on the robot arm, so they can see what's going on with the surgery. And in their hands are controls where they can actually physically control the robot arms and determine what they do. They can perform incisions, they can take out, biopsies, whatever it is that needs to be done. This can all happen from these two doctors sitting at these stations. Now, in this picture, these doctors are in the same room with the patient, but there's really no reason that they have to be. And in fact, there are now systems where these doctors can be anywhere in the world and the patient can be anywhere in the world. And this allows access to many more people across the world to get medical care that they otherwise wouldn't be able to get. But again, I'm a cybersecurity person, and I look at this and I say, well, when the doctor's in the same room, maybe you have a wire going from that computer to the robot arm, and there's really no way anyone could interfere with it. But in fact, these things are using TCP/IP, they're using the internet. And oftentimes when we think about security, we're concerned with confidentiality, we're concerned with integrity, and obviously availability. But never is denial of service and availability more critical than when you look at an example like this, where if you were to knock out the network between the surgeon and the robot arm during the middle of a surgery, you could cause great harm to that patient. And so it's very important that the companies that build these things focus on security and understand what the security risks are. The next item that we look at is a dialysis machine for home dialysis. And this used to be a treatment that required someone to go into a medical facility, spend a lot of time there, expose themselves to possible germs that other people might have had in the hospital. But this device can sit at home and provide the same dialysis service. And it's obviously smart. By smart, we mean connected. It has running an operating system and applications, and has remote access capability. And so all of the cybersecurity concerns of the infusion pump can go with this. I just wanted to show one more example of a cyber physical medical system that is starting to be seen in people's homes. The next one that we have here is a glucose monitor, and this is something that someone who's diabetic would probably have, and they can then usually control the dosage of insulin that they give themselves through a pump. And this is technology that's already been around a little while and is being really developed and revolutionized now into much more sophisticated systems. And the last one here is an implantable defibrillator and a corresponding app. So now it really doesn't take any imagination to see why the cybersecurity implications are so important here, because we're talking about something that's connected to your heart inside your body, which you can control through an app, usually over low energy Bluetooth or something like that. And so obviously, if you could interfere with that process, you could cause a lot of damage. And there was a research paper almost 10 years ago now, if I'm not mistaken, that talked about these types of attacks. They actually bought a bunch of ground beef and put a defibrillator in it to simulate. They weren't able to find any volunteers who had these things, so they had to build a simulated environment, and they were able to change the treatments in there, the patient's name, all kinds of things like that. Since then, the medical device companies have greatly improved their security, and I believe they take it very seriously. Furthermore, the FDA is very good about their standards and their requirements for security. So let's look at this robotic surgery system and see what the attack surface could be of such a complex system. You have the robotic surgical arm, and then you're going to have some third-party smart device. Maybe it's a phone or a tablet that is sharing information, possibly even controlling it. The control application is where we saw the doctors sitting there performing whatever action they are, and that needs to communicate securely with the system. There's going to be a local server which is going to have logging and information about what's going on with the procedures, and a local way to store information in case maybe you get disconnected from somewhere. There's a electronic health record system which has to be kept for billing purposes, for purposes of understanding all the activity that took place. In the robot example we talked about a minute ago, there are also things like cameras, and those are usually going to be smart cameras with IP addresses, and so they also represent a point of attack into the system. There's going to be a cloud component, as I already mentioned, in order to store information so that it can be accessed by other parties, and other connected medical devices which may be interfacing with it. So you can see that this is actually a pretty complex system, and all of it has to be secured because the weakest link is the one that is going to be attacked. And so you want to make sure that each component doesn't represent that weakest link. One of the things that I like to do when looking at a medical device and trying to help a manufacturer build security is to build an attack tree. An attack tree is a data structure that lets you analyze all the different ways that someone might attack the system. So at the root, we have unauthorized access to medical device. So how could that happen? Well, one way might be through physical access, another might be through remote access. And then you break down, well, what kind of physical access? Well, there could be a touchpad, there could be a QR scanner, a USB port. And this attack tree here is just to be exemplary to kind of show you the concept. But in reality, these, you can have, pages and pages, dozens of pages of graphs when you have a real attack tree for a medical device. But the attack tree is a useful tool for understanding the threat model and understanding where security needs to be kept. And I should point out that there are reasons why these medical devices might be attacked and why they can be such high value targets. One is, as I mentioned, they have personal health information. And I heard an estimate that on the black market, a medical record, one single medical record can go for $10 if you have legitimate records. And so if you can steal, tens of thousands of records from a hospital, that could be quite valuable. Why? Well, attackers will use it for identity theft. It could be used for blackmail. There are all kinds of reasons why an attacker might want someone's personal health information. The billing and insurance data obviously controls how the money flows, so that's a target. One that you might not hear a lot about, but is very important, is the intellectual property of the medical device manufacturer. So they put a lot of money, billions of dollars, into research and development to build their medical devices. And what they don't want is a competitor to buy one of their medical devices, tear it open, figure out what all their algorithms are, and then build a similar product without the need to pay for that investment in research and development. So one area of security when my company works with medical device manufacturers is how do we help protect their IP? A pivot point is the idea that one device can be used to launch an attack into another device. So let's say that you have a bunch of medical devices in a home, for example, and the home you've done a good job securing the home, but one of the components of your system has a vulnerability in it. It may be easier to attack the other parts of the system from there than it is when you're remote. For example, you could maybe read the local LAN and see the IP packets that are traveling on the LAN and figure out how to compromise the system that way. Last but not least, something that really gained its footing in the medical space is ransomware. And I think everyone's familiar with ransomware, but it's the idea that that an attacker will hold something hostage, like your data, and will only give it if you pay them a certain amount of money. Now think about a medical device, think about getting a message on your phone saying, well, something that might be a little silly would be, it could say that your infusion pump just gave you a lethal dose of medication. if you pay this Bitcoin to this address, then it will dispense an antidote. Now, most people would realize that that's not really possible, but not everybody. And if you're connected to that machine, that could be awfully scary. Or it could do something simpler, such as refuse to work unless you pay something and you know that you need your medicine. So ransomware, when you're talking about a medical device that's connected to a person or an implantable, like inside next to your heart, those can be quite profitable for the attackers if they are able to scare them. And there are other things that attackers can do. For example, they can forge patient data. I talked about the denial of service attacks against the robotic surgery, and that's just one example. Also imagine if a doctor is using an electronic prescription service and you block the networking there, then you wouldn't be able to buy your medication. Stopping the clinical functions of a medical device is a critical attack. There's a story that Dick Cheney, when he was vice president, had 2 implants near his heart that were used to help him with his heart problems because he had had several heart attacks. And that at one point, the Secret Service decided to turn off many of the features of his devices because they were actually worried about another country hacking them and killing or hurting the vice president. So this stuff is real. These are just operating systems. Many of them have embedded Linux running. And so, these are serious targets. And here's a list of various things that the attackers might try to do. I've heard it said that root access to the critical care system is basically getting root access to the patient. So that's the concern that you have, is you don't want someone to root you. Now, the medical device industry has come a long way. When they first started building some of these medical devices and adding network connectivity, they weren't security experts, but they quickly learned that you don't want to read about a vulnerability in your medical device in the New York Times because your stock price, and there have been cases of stock prices being cut in half on the same day that there's an attack. And so obviously we care about people and patients, but companies also care about their reputation and their bottom line. Investors don't want to invest in something that's plugged into a person that's been hacked. So there are a lot of reasons why companies care about security, and it's not all the goodness of their heart. They also have to go through a rigorous approval process in the United States. That's the FDA, which has all kinds of regulations about medical devices. And I believe the FDA is actually quite good at this. The FDA has several top scientists doing rotations through there. They have relationships with professors at various universities that are involved in some of their approval process. And they periodically update their standards to meet the newest threats. And so I think we're fortunate that everybody is taking this so seriously, and in particular that we have the FDA that we have. So let me do some case studies now. And these are case studies where Harbor Labs, my company, worked with a medical device manufacturer to try to help them. So the first one I'm going to talk about is a portable defibrillator. This is something you may have seen at the airport or in various places, and it's intended to revive someone whose heart is out of rhythm, and this is a life-saving device, really. So one thing to consider is the medical device is built, and the manufacturer runs a cloud farm in order to hold the data. And sometimes this medical device needs a software update. Maybe we're in that process I talked about where a vulnerability is discovered and the manufacturer needs to patch it. And so one of the things that the manufacturer has to submit to the FDA is what is their patch process that they're going to use. And so this manufacturer, before they started working with us, they designed this process where the device requests a patch from their cloud and the patch is sent back. And this was unauthenticated, so they did not receive approval for this device. So they tried again, and they said, okay, well, let's just sign it. So they had a hardware security module in the cloud, and they signed the patch, and the patch was returned to the device. The problem there was that the device could have been the patch could have been tampered in the cloud before it was signed. So the FDA did not approve that. So next, they designed a system with a patch request. They had an on-prem asymmetric private key generation and patch signing system so that as the patch is exported into the cloud, it is signed, and then that signature is sent back. Does that seem secure? It might, but the FDA said no, we're not going to approve that because it's subject to a replay attack. And what is that replay attack? Well, let's say that there's a particular patch, and then that patch gets signed and sent to the medical device. And then later someone discovers a vulnerability in the patch. Even if that's fixed, someone could come and then when that patch request for the new fix is made, they send the old patch, not the new one, and it's signed. And so the device might believe it and then put a vulnerable patch in. So then they came and they hired us and we looked at their system and we said, well, you guys are close, but what you want to do is have this system where the patch is signed, but then it's timestamped and the timestamp is in the signature. And then you have an authenticated patch with a nonce, which is a one-time identifier. And then they got their FDA approval. So you can see that the FDA actually, they don't apply cookie cutter processes. They have experts look and they're familiar with all the types of crypto attacks and protocol attacks, and they are able to come up with a system that's much more secure. All right, the next one we're going to look at is a wearable insulin pump and secure cloud connectivity. So here we consider that there's a personal medical pump. This is something that is actually connected to the person through a needle and is going to dispense insulin when the person needs it. The model is that the user uses their phone or their medical device, and that the manufacturer of this personal medical pump has a cloud service. So one of the regulatory requirements is that the pump can be configured using the mobile device, but that the data that's transmitted from the medical pump to the cloud service cannot be read by the mobile device. And the reason is mobile devices might have been compromised, or they may be running malware or something like that. And so what happens is you have an encryption that's end-to-end from the medical device to the cloud. So your connection, you have a secure and authenticated connection between the device and the personal medical device. So that could be like a Bluetooth pairing using a cryptographic protocol. And then you consider the fact that the personal medical device has personally identifiable and personal health information. The mobile device doesn't. It's just used to configure the personal medical device. And then that information is sent via the mobile device, which can't access it anymore, to the cloud provider, which can then put it into, for example, a portal. So we had a client that was building a system like this. And so they built a way to automatically pair and authenticate and encrypt the data between the device and the medical device. Then they established end-to-end authentication and encryption. You can use something like SSL for that. And they received their FDA approval. The last case study that I'm going to talk to you about is a drug infusion pump. And this is a device that can pump medicine into a patient in their house or in the hospital. So in the early generations, these things have been around for quite some time. So the earliest generation, which I won't even talk about, were standalone devices. They weren't networked, they weren't smart. They just were machines that could dispense medication based on a timer. Then there were, those evolved and there were networked versions of these. So you could have a single set of access credentials, and they didn't really do a good job of securing various protocols. In fact, they had unencrypted telnet, and these things were widely criticized in the press because they were released with internet connections, but they weren't built securely. There was a USB port that could be used to configure and maintain it, so that couldn't be done remotely. But one of the interesting features of them is if you could get to the keypad, you could control the medications on these devices. And another thing is they only had one operating system. So if there was a problem at the network layer, that could be used to interfere with the clinical operation of the device. So very scary. So in the earlier generation, there was no differentiation between users. Every user was a user, and there wasn't like a super user or an admin. There was just a user. If you could get to the USB port, you could change the software on the system. There were open ports. So if you ran an Nmap on this thing, you would find all kinds of vulnerabilities. And again, if you were doing an operating system update at the time that you were supposed to be dispensing medication, then you were out of luck. So the systems that we have today have much better security. They have different accounts for different services. All of the unsecure services like plain text telnet have been removed. If you have physical access, you actually need to know a PIN. So if you leave this thing unattended in a hospital, someone can't come and just change the software on there or the prescriptions. All of the communications and clinical operations are partitioned into two operating systems. So typically, they'll run an RTOS, a real-time operating system, which is often proprietary, which controls the clinical operation. And then they'll run something like embedded Linux for the management of the device. And those two have a very, very limited interface between them. So whenever you're in management mode, all the clinical operations are disabled. And there's really no way that if someone compromised through a vulnerability in the embedded operating system, that they could change the clinical operation of the device. And that's the key, to separate those out. And so once that's done, these types of devices can get FDA approval. So let me review a little bit about what I talked about. There's the risk mitigation of looking at a medical device, designing an attack tree, and defining a threat model. This process right today cannot be fully automated. So you want to get smart people who know how to think, who understand the threats. The FDA is going to use smart people. They don't have an automated process. They have many tools, but at the end of the day, it really comes down to a human doing this. And up until now in this talk, I've really focused on medical devices and the healthcare system. But there's a similar thought process that applies to other domains such as banking, transportation, communications. So there are many different areas where similar processes applies. And so you need to consider which threats are specific to your application. So let me just summarize a little bit about medical devices. Obviously, they are continuing to grow in complexity. We're going to see them proliferate. I think that COVID has accelerated the move of devices into the home because people don't want to go out and get exposed. And so medical device manufacturers are looking at more and more things that can be done at home, which also means smarter, more connected devices and increased risks. But we do have a class of security experts now that are learning a lot about medical security and are applying it to these manufacturers so that their systems are actually coming out pretty good. And we can thank the foresight that a lot of the people at the FDA had for designing processes that wouldn't get very insecure systems through. And we need to continue to devote resources so that medical devices will be focused on security. So that is the end of my prepared remarks. Thank you very much. And I'm opening it up to questions.
Yeah, thank you, Avi. That was very interesting. So I'm curious. I'm going to start our Q&A section off. What type of threat actors do you see in this field?
So that's a really good question. The threats, many times those threats are theoretical, and we look at the design and say, well, what if there was this threat, or what if there was that? But you know, there are many systems that had theoretical threats for a long time before anyone actually implemented the attacks. And so I think we need to design the systems to be secure, regardless of whether they're actually getting attacked or not. The other thing is, think about state actors. You know, our relationship with Russia is deteriorating. We have countries like Iran and North Korea that would love to attack us. And the more you combine the cyber with the physical, the more you run the risk that someone can attack you from abroad without any accountability, without even being able to figure out where it came from, and cause some damage in the real world. So as we plug more computers into people, And as we connect more devices on the internet, we have to really ask ourselves how secure it is. And we need to consider, like, are these attacks really happening? But I don't think that the answer to that should guide how we proceed.
Huh. Yeah, that's an interesting take. I mean, physical system security is obviously a growing field, and especially in medical devices. I mean, that's pretty integral to protect. So another question was, since medical devices have long lifespans, it's hard to anticipate future avenues for attacks. And should the logic portions of implants be separated more?
That is a fantastic question. And in fact, medical devices are really, really expensive and they're designed to last a long time. I looked at an ultrasound machine that's 25 years old that's still being used. In order to replace it, a medical practice, would need millions of dollars, which they don't have sitting around. But I think the newer medical devices are being built with different priorities other than like lasting a long time. And in fact, while the hardware will last a long time, they're often being updated with software all the time. On the other hand, consider something that gets implanted into your chest. You want to make sure that you have to pull that out as infrequently as possible. And so if you have a patient with an expected life span of 15 more years, and you can put something in there that lasts at least that long, you'll be doing them a great favor versus if it only lasts 2 years and you have to open them up again and put them at risk of all kinds of infections and complications from surgery.
Oh, interesting. Thank you. And so, as far as trade-offs when looking into security, because oftentimes we see that security is many times an afterthought, right? So, what's the trade-off of making a priority, which is what it sounds like the FDA is doing?
Yeah. So I think in classical security, where we're not dealing with medical devices, we often will trade off risk and reward, right? So you could say, well, if I put in $200,000 worth of security, probably won't have an attack over $1 million. And if I put in $500,000 in security, I won't have an attack over $500,000. And you can kind of say, well, I'm willing to get hacked every once in a while because it's not going to cost me that much, and I don't want to spend that money up front. But you can't put a price on people's lives or people's health. And so the math kind of doesn't work when you look at doing a risk assessment. No, you don't. The number of acceptable people dying from insecurity of a medical device is zero, right? And when you look at banking, they take a certain amount of loss in that industry and they just attribute it to the cost of doing business. But that shouldn't be an option with medical devices.
Yeah, for sure. I mean, especially when you're dealing with human life rather than other systems.
Yeah.
And so we have another question from Ernie. What is your opinion on Fitbits and other similar personal type devices that are starting to get closer to medical devices?
Yeah, absolutely. So this is my Apple Watch, and I've had a Fitbit. I'm a computer geek at heart. I love technology, and I'm the first one to buy the next coolest thing that comes along if I think it'll be useful. But I'm very well aware of the security risks. So this is a classic case of the trade-off we were just talking about. I know that there is some small chance, or maybe not so small, but there's some chance that someone could hack into my Apple Watch and mess me up, like make me think I'm jogging faster or slower than I am, or that it's a certain time when it's not, or even maybe burn my skin by turning on all the sensors a lot more than they're supposed to be. But I don't think those things are that likely. On the other hand, all the utility I get from it and all the benefits are 100% likely. So I think it's great and it's worth it. And if the device got attacked, I'd probably be less surprised than most people. I'd say, well, yeah, it's just running software and I believe it can get attacked. But you just have to ask yourself. Like, I went out and got a Nest doorbell because I thought it would be great to be able to, see when packages are delivered and talk to people if I don't want to answer the door. And I know it introduced a new device into my home network, increased the exposure of my computers, but I actually did some configuring on my home firewall, taking that into account, partitioned my network to like a network that connects to IoT devices, and then my inside network, and they all connect to the internet separately. So there are some steps that you can take, but I think at the end of the day, it's a kind of a personal decision about whether or not you want the benefits of something and are willing to take those risks.
Yeah, thank you. And so a similar type question, is privacy implications of the implants considered much, and near field communications being detected at farther ranges and are distinguishable signatures and so on?
Yeah, so definitely all of that is important. Patient privacy is critical. If you think about biometrics, actually, which wasn't the question, but I think it's related. You only have 10 fingerprints, right? And so once those are compromised, then you can't generate a new one. It's not like a password that you can change. And same goes for if you have an implanted device and someone compromises the information about the patient in there, it's not something that can easily be changed or swapped out. I think that even the fact that you have an implant could be a privacy concern for you, because of various things you might want to do that you may be prevented from doing because you have an implant. Obviously, I think at the airport, you're going to have to tell them that you have it, but we shouldn't create situations where people have to disclose more than they absolutely have to.
Gotcha. Thank you. And shifting gears a little bit, what happens if a medical device manufacturer goes bankrupt and no one is providing patches and updates for these devices?
Well, you got a really good group of people asking these questions here. So that's a tough one. And I think that the answer to that is that you want to stick with the big guys, really. And that's tough because a lot of the innovation happens with smaller companies that will come out with something. And I'd say that if it's a device like a glucose monitor, the decision process is different from like an implanted defibrillator, right? Because at the worst case, you wasted some money with a glucose monitor and you could buy a different brand. But if you have a pacemaker or a defibrillator that's implanted and that company goes out of business, yeah, that's a problem. Probably no one's going to support the patches. And if you go with the tried and true with the really big guys, and let's say they do go out of business, there's going to be a secondary market of companies that are going to come up to support those, because American capitalism is great in that anytime there's a demand and someone's willing to pay for things, someone will come meet that demand and build it. We see that with a lot of industries where there's repair or support services that come up that are different from the manufacturer because there's a market for that.
Yeah, of course. That's an interesting take. And it's definitely something that's probably more prevalent in medicine than other fields.
So,
And so in the medical field, hospitals still are using pagers. What are your thoughts on that?
I think there's a certain amount of, if it works, keep using it. If it ain't broke, don't fix it. And they've had pagers for a long time. I actually think that in the more tech savvy kind of modern wealthy hospitals, they're probably using different technology, maybe smartphone based. But a lot of times the budgets in medical facilities are kind of fixed, and they can cover all the things that they need to do day by day, but their long-term capital budgets are rarely updated. And so let's say you had a system with all the doctors having pagers and you have a server that manages that, and you want to replace that whole thing and the way of doing things, you need money for that. And so I think it creates a bigger divide, I think, between like Johns Hopkins Hospital and a place that's in a remote rural America that is barely getting by. The different abilities for them to adopt newer technologies.
Interesting. And kind of similar, almost like a jump board off that question. How do you go about securing older devices? So obviously kind of similar to the last question, where if they're bankrupt and they can't put patches, but with devices of older hardware that are meant to be long term, how do you go about securing those devices? Similar to what you're saying about the vice president's chest implants, those are not really too accessible.
Yeah, another excellent tough question. I think that there are some devices where it's not an issue because they're old enough that they're not connected and you don't have to really secure them except for maybe physical security. But if you're looking at the early generations of some of these connected devices, they really should just be sunset and put aside. Again, you have to look at the trade-offs of different types of devices. So if you have an ultrasound machine maybe you don't get rid of it. Maybe you just want to turn off the internet on it and say, okay, we're going to use this here, but then we're going to walk this disk over to a computer and upload it so that this machine isn't connected to the internet. I think the time frame for updating devices should be small when possible. And every type of device has to be looked at individually to figure out the cost calculus, the the clinical importance of the device and the risk.
Yeah. So it sounds like, just like with everything, it's really just a matter of risk management and seeing how far you can go and what's acceptable.
Absolutely.
And so moving on to Matt's question, should right to repair laws apply to medical devices then? A device might have keys to prevent it from being updated, and I worry if they go bankrupt and those keys are not disclosed, it leaves significant challenges to create updates by third parties.
Yes, I've been in touch actually with the Right to Repair organization and the lobbyists that they have, and I'm a very big fan of theirs. I think that it's an issue which I can intellectually see both ways, but I feel kind of ethically and morally and just what's reasonable and fair that anything that you buy, you should own and you should be able to tinker with it. And there are many reasons. One of them is sort of just like an American feeling that we have freedoms, and I have a device and I paid for it and I should be able to do whatever I want with it. I also think, and I'm going to give you a flip side to this, but I also think that, like you said, the risk of a manufacturer going out of business and there not being any expertise in order to continue to maintain something is real. The flip side is that there's a community of do-it-yourselfers with glucose monitors and infusion pumps that have really done a very impressive job of reverse engineering these things and building all kinds of tools and their own patches. There's some risk associated with that because you might get software from an enthusiast and it hasn't been tested at the level that the manufacturers do, or it hasn't been FDA approved, or maybe it works great until the manufacturer issues a patch and then that breaks it. So there's a danger of not knowing what you're really getting. And I don't want to discourage people from doing that. I just think it needs to be open and transparent. If you should understand the risks of doing it yourself. I don't think it should be a law against it. I should be able to do whatever I want with my devices, with my body, with myself. But I also think I should have the right to know if the thing I'm getting is the vanilla manufacturer one, or if it's been tinkered with or tampered with.
Thank you. Yeah, and so in medical device security, are there any concerns in the supply chain of the parts going into it and so on, or is that mostly something more concerned so in other sorts of physical system security instances?
I'm not sure how much of the medical device components are sourced in the United States or abroad, but obviously this is a real concern. China has shown that they can come in at any level, whether it's the hardware, the BIOS, the firmware, they will implant back doors, and not just picking on the Chinese. I've just seen many examples of that, and there are others that would do it as well. And considering there are state actors that would harm us, I think that that's a legitimate concern. It's a reason to maybe have companies with background checks and with various clearance type levels providing components for very sensitive things. But if you just buy from the cheapest international vendor your hardware and you stick it in the devices, it's a real concern that these things could be compromised more easily or have behavior that was not intended.
Yeah, that's interesting. It's clearly becoming something that's been growing, where we're just seeing state actors and those sorts of hacking instances just keep growing and growing and growing, and it's definitely becoming a bigger and bigger concern.
Yeah, I mean, it sounds like you and your audience have done your research and are asking all the right questions.
Yeah. Well, thank you. And with that, do you have any final thoughts or comments to impart with us?
No, I just appreciate the invitation again. I'm a big Go Blue fan. Enjoyed the last basketball season. hoping for a good football season, and also just enjoyed sharing some time with you and talking about my work.
Yeah, thank you for joining us. We really appreciate it. And